Okay, so let's take a look at an example using the 7 steps in NHST, and we'll use the scenario on the screen. Basically, a researcher, let's say, is interested in looking at the impacts of long-term alcohol use on IQ, and specifically, she hypothesizes that individuals who use long-term alcohol or use alcohol long-term are going to have a lower IQ than those who don't. And she samples 230 self-identified long-term alcoholics. She gets their IQ score on the WAIS-4, we'll say, which is a standardized IQ test, and she discovers that their mean score for long-term alcoholics anyway is 98. And so what we want to know now is her hypothesis valid? Okay. Is the use of long-term alcohol associated with a lower IQ compared to those who aren't? Now, in order to make any kind of comparison, we have to know what is the average IQ score for a non-alcoholic population. Well, fortunately, because the WAIS-4 is standardized, we know that it has a general population mean score of 100 and a standard deviation of 15. So now we want to compare our sample to this population value that we do know. And some of you may be tempted to say, well, 98 is less than 100. We can stop there and say, hey, long-term alcohol use ends up with lower IQ than non-alcoholic use. However, we still don't know at this point whether the 98 being different from 100 is statistically significant. It could just be sampling variability that we are likely to get anyway. What we want to know is it statistically different, significantly different? And so in order to test that, we have to run our inferential tests. So let's start with step one. Let's identify the different hypotheses that we can possibly have here. So the first hypothesis, the H naught, is our null hypothesis, which says there is no effect. In essence, the IQ for a population of alcoholics is identical or equal to, roughly, the IQ of non-alcoholics. Okay, and that is our null, and again, that's what we're always testing, is whether or not there is a significant difference. Our alternative hypothesis, if I can spit that out, is that long-term alcoholics are going to have a lower IQ than non-alcoholics. And you'll see the little asterisk next to this, which indicates this is our hypothesis. But the opposite, or the other end, could also be true in the fact that, maybe alcohol use causes a higher IQ. So the hypothesis we want to list for that is the IQ for the population of alcoholics is actually greater than that of the population for non-alcoholics. Again, because we want to leave both sides open, or both ends open as a two-tailed test to see what the implications are. Okay, so that is our hypothesis. Step two, examine the data and decide on the statistical test. So far, we've not done anything other than z-scores, so by process of elimination, that's what we're going to use, though in the future, you will have to make a better choice between or on step two. There will be a point at which you need to be very critical in your selection of the test, because you can run the wrong analysis on your data and reach the wrong conclusion, which is not so great, especially if you're in your dissertation phase and you've written all this up and you're ready to defend and it's the wrong analysis. So right now, it's a pretty simple choice. It's just a z-test, but in the future, you're going to have to make some choices and make sure you're making the correct choices. So step three, we want to choose the critical p-value, which, as I said before, unless otherwise noted in social sciences, it's always going to be 0.05. There are rare cases where it's not, but generally speaking, it's 0.05. And so at this point, I encourage you to draw out sort of a rough graph of your curve, because we want to highlight where we are to help us make the right decisions. So we put this out. We know that we're going to use a p-value of 0.05, and again, because we're using two tails, we want to split that 0.05 equally, put half of it on the negative side and half of it on the positive side. So we could draw our little line here and put p equals 0.025 over here and shade this in, because this is the area we're looking for. And then we would also do that over on this side, where we can put p is equal to 0.025 here, and we're looking for this area. So again, 0.025 you add together and you get your 0.05. We're looking for the probability of getting these scores or these scores before we're going to say that our result is not likely due to just random sampling. Okay, but again, P of 0.05 is what we're looking for. So now we have to, sort of the subpoint here is obtain the critical value, or the value that is associated with this P of 0.05. That's the probability of getting a value here, but what is this Z value at 0.025? In order to do this, then, we've got to look at our Z table. As I mentioned before, we can, hopefully you will commit this to memory and know whenever you see this value, you can immediately know what the Z-score is. But if we didn't know what it was, we can simply look for the probability of the smaller portion that is equal to 0.025. So in this case, we're going to be looking for the values in the smaller portion section. And we could go down that right column there, that right set of columns, I should say, and go down until you find a P that is equal, or a value that is equal to 0.025. We find that value near the bottom. You go over to the left a little bit, and we find that the Z-score is a 1.96. So the Z, and we'll say this critical, so Z subscript crit is equal to 1.96. Now, remember, whatever we do to this side, we would also do to this side. So this Z critical over here would be equal to a negative 1.96. So the easiest way to sort of write this is that our Z critical is equal to a plus or a minus 1.96. So we are looking for values at either end of this distribution to say, hey, this is statistically significant. All right, so we've got this shaded in. We know what we're looking for. The next thing we want to do is actually conduct the analysis. So normally we will let SPSS run this for us, but we want to walk through this by hand at least once, just so you kind of see where these values are coming from. And we're just basically going to plug and chug numbers into this formula. So if we look at this formula, we see X bar, which is our sample mean. We know from our scenario in this case that it was 98. So 98 minus our population mean, which we know here is 100. Okay, so 100. And we're going to divide that by our standard deviation for the population, which is 15. And we're going to divide that 15 by the square root of our sample size, which we know was 230. Okay, at this point, it's just simple math. Go ahead and get out your calculator if you don't have it. It's good practice to just follow through this. When you meet face to face, I'll have you actually using your calculator some. But basically, you're going to work this out. In the end, we find that this is going to be a negative 2 over approximately 0.99. So our value at this point, our observed Z-score, is going to be roughly equal to 2.02 negative. Okay, so I'm going to put that over here. So our Z observed, which you'll see is a Z subscript OBS, Z observed, is equal to negative 2.02. So again, I want to plot this on our little graph just so that we're making the right decisions, and you can see this because it is a little confusing as you start this journey on statistical analyses. So where does negative 2.02 fall on our graph? It is somewhere over here. We know this is negative 1.96, so it's going to be further this way, just barely. But let's say it's somewhere right in here. Okay, so we now know this is our Z critical, it's right here. Okay, so we've got our observed value of negative 2.2, but we also need its related p-value. So let's find that. If we go to our Z table here again, we're going to be looking this time for a Z-score of negative 2.02. But you note on this table there are no negatives. Recall again, whatever you do to one side, you do to the other. So all we have to do is find the positive 2.02. Well, if you look, it's in that right column almost near the bottom. We go down to 2.02, move over to the smaller portion, and what do we get? We get 0.02160. So this is going to be, let's put it over here, 0.02160. But that's just for one side. Whatever we do to one side, we have to do to the other. So basically, you're going to end up doubling this. So instead of 0.02160, it's basically going to come out to 0.04320. So our P observed is going to be equal to 0.04 to 2 decimal places. So P observed is going to be 0.04 if we round to 2 decimal places. Okay, so again, our Z critical, we were trying to hit plus or minus 1.96. What we actually hit was negative 2.02 with a related observed p-value of 0.04. Now the second piece to this, as we go to step 5, is we want to compare the observed p-value to the observed critical p-value and draw our conclusion. Okay, so here are our observed critical and observed z-scores. Here's our observed p-value, but what was our critical p-value? In this case, we were looking for a p that was 0.05. Okay, and I should say more specifically, we were really looking for p-values that are less than or equal to 0.05. So if this is 5%, our score is only likely to happen 4% of the time in the long run. So what this means is if I took enough samples from the population of non-alcoholics, okay, and just randomly sampled 230 participants over and over and over and over and over again, and I did this repeatedly for the long term, only 4% of the time am I going to get a z-score of negative 2.02. Because that isn't likely to happen regularly, okay, it only is likely to happen 4% of the time. 4% of the time I'm going to get a negative 2.02 or more weird. Because of that, I'm going to conclude, well, this is a low probability of that particular score, so we're going to call it statistically significant and say, this difference in IQ really is due to some characteristics of long-term alcohol use. Okay, so our conclusion then is, hey, our hypothesis was correct. 98 is less than 100, and it is statistically significant. Therefore, we can conclude that long-term alcoholics have a lower IQ than non-alcoholics. So let's go on then to number 6, and I'm going to slide over here a little bit. Erase these values here. And let's calculate now the effect size. In this case, we're going to look at Cohen's d. Okay, and we're just going to plug in these values again and plug and chug. So what is our mean? Our sample mean was 98. We know our population mean is 100. And we're going to divide this by the standard deviation for the population, which we know was 15. So 98 minus 100 divided by 15. You can do this on your calculator. Basically, what you're going to get is 0.13. All right. So our little d, let me erase this now. Little d, Cohen's d is going to equal 0.13. All right, so 0.13. As I'm looking at this on the screen, it doesn't really look like a 3. So it's 0.13. So Cohen's d is 0.13. And now the question is whether this is small, medium, or large. For small effect sizes, for D, it would be anything hitting 0.2. If it's less than 0.2, we would say it's really tiny. At 0.5, it would be medium. 0.8, it would be large. In this case, it doesn't even hit the 0.1 or the 0.2. So we would say this is really tiny, but we could just say it's small. But we know it's really small. And if you think about this, really, 2-point difference on an IQ test, is that a big deal? Not really. So it is a small effect. So while we would say it is statistically significant, practically speaking, there wouldn't be much of a difference in the average IQ for long-term alcohol use versus a general population. Okay. And finally, the last step then is we want to construct our confidence intervals and interpret them. Okay, so here is our value. Again, let's look at the formula, and I'm going to put it inside here. So our mean, again, is 98, and that's going to be plus or minus our Z critical, which we said was 1.96. So 98 plus or minus 1.96, and we're going to multiply that by our standard deviation for the population over the square root of our sample size. So 15 over the square root of 230, which was the number of participants that we had in our study. So again, it's 98, our mean, plus or minus 1.96 divided by our 15, our standard deviation, over the square root of our sample size. If we calculate everything to the right of this plus or minus, we're going to end up with 98 plus or minus 1.94. Okay, hopefully if you're using your calculators, you're tracking with me, and hopefully I haven't messed up, which is not a guarantee. But we've got 98.14, so the first thing we want to do is take 98 minus 1.94, and that's going to give us 96.06. Okay, that's the lower bound. And then the upper bound is going to be 99.94. So what we would conclude with our confidence interval, and by the way, this is a 95% confidence interval. Again, because we're using the P of 0.05, the inverse of that for confidence intervals, just note it's 95%. So we are 95% confident that this range right here, 96.06 to 99.94, contains the true population value of IQ for long-term alcoholics. So, question I have is, would we consider this sort of a narrow range, middling range, or is it broad? Well, if you're talking the total swing here is about 3 IQ points, I would say that's pretty precise or pretty narrow. Okay, so we have a pretty confident value that the actual value for long-term alcoholics is somewhere around 96 to almost 100. Okay, and that is our 7 steps for NHST. And hopefully that makes sense to you. If not, we're going to run through this multiple times. You will get much better at this, but you are certainly welcome and may want to watch this video again.